In 2017, particle detectors found a lower density region above the Great Pyramid's Grand Gallery at least 30 meters long. 3 detector systems confirmed it, no doorway leads into it, and no explorer has entered it. After 2 centuries of study, why does this monument still contain a space this large, and what was it built to do? That is the real mystery of the Great Pyramid. Not who built it, not whether ancient Egyptians were capable of building it. Archaeology has answers to many of those questions, and some of the evidence is remarkably direct. The harder problem is that the better we become at looking inside this monument, the more its internal architecture refuses to become simple. The Great Pyramid was built for the pharaoh Khufu during Egypt's 4th dynasty, more than 4,500 years ago. It originally rose to about 146 meters. Even after losing its outer casing and part of its summit, it still dominates the Giza plateau. Its footprint is enormous. Each side of the base stretches roughly 230 meters. The monument contains millions of blocks, most of them local limestone, while harder stone such as granite was used in some of its most important internal spaces. For centuries, those numbers encouraged a particular kind of storytelling. The pyramid became so large, so old, and so precise that its builders were gradually pushed out of their own achievement. Popular accounts replaced them with vanished technologies, unknown civilizations, or knowledge supposedly too advanced for ancient Egypt. The archaeological record tells a different story. At Giza, excavations have uncovered settlements, food production areas, administrative remains, tools, and cemeteries connected with the workforce that supported royal construction. These were not mysterious outsiders, they belonged to the society that occupied the Nile Valley during the Old Kingdom. And far from Giza, on the Red Sea's coast at Wadi el Jarf, archaeologists found something even more revealing. Among a collection of papyri was the logbook of an official named Merer. His records describe a work crew transporting fine limestone by boat from the Tura quarries toward Akhet Khufu, Khufu's horizon, the ancient name associated with the Great Pyramid. The document does not explain every stage of construction. It does not tell us exactly how the highest blocks were raised, or settle every argument about ramps and lifting systems. More importantly, it does something else. It places organized Egyptian work crews, stone transport, royal administration, and Khufu's construction project in the same historical world. The builder's not missing. Their complete engineering manual is, and that distinction matters, because the Great Pyramid does contain genuine problems without inventing new ones. Start with its orientation. The sides of the monument were laid out astonishingly close to the cardinal directions. Its north face deviates from true north by only a few arc minutes. Achieving that with no satellite positioning, no modern surveying instruments, and no magnetic compass required an observational method of extraordinary consistency. One influential explanation was proposed by Egyptologist Kate Spence. Instead of assuming some lost instrument, she asked whether the builders could have used the sky itself. Around the time of Khufu, there was no bright star sitting exactly at the north celestial pole as Polaris does approximately today. Observers could instead watch circumpolar stars rotating around that invisible point. Spence proposed that Egyptian surveyors may have used the alignment of 2 such stars to establish a north-south reference line. The hypothesis produces an interesting result. Because Earth's rotational axis slowly changes direction through a motion called precession, the apparent alignment of those stars shifts over centuries. When the orientation errors of several Old Kingdom pyramids are compared with their approximate construction dates, they follow a pattern that is broadly consistent with a stellar method. That does not mean the case is closed. Ancient surveying techniques remain debated and other methods have been proposed. What it shows is more useful than a claim of impossible technology. Extreme precision can emerge from careful observation, repeatable procedure, and skilled labor. The same principle applies to the stone itself. The Great Pyramid was originally covered with fine white Tura limestone casing, creating a smooth outer surface very different from the stepped core visible today. 19th century surveyors, especially Flinders Petrie, documented the monument with an accuracy that still makes his measurements valuable. Some surviving casing joints were extraordinarily tight. That workmanship deserves attention. Precision, however, is not evidence of machinery for which archaeology has left no trace. Stoneworking tools are part of the archaeological record. Copper implements, stone hammers, abrasives, and quarry evidence survive from ancient Egypt. The real technical debate is about how combinations of known materials, organization, leverage, transport, measurement, and labor were applied at this scale. That question is difficult enough. There is no need to replace it with a civilization that vanished without evidence. Yet even once we accept that Khufu's Egyptians built the monument, another problem remains. We can identify its historical setting. We can reconstruct parts of its labor system. We can trace stone coming from distant quarries. We can study the geometry of the exterior. Then we go inside. The known internal layout is unlike the simple solid mass suggested by the pyramid's silhouette. A descending passage cuts down through the masonry and into the bedrock. Ascending passage climbs toward the heart of the monument. The grand gallery rises above it with a high corbelled ceiling. One route leads toward the chamber, traditionally called the Queen's Chamber. Another continues upward toward the King's Chamber, built largely from granite. Above that chamber is a sequence of spaces formed by massive stone beams. Narrow shafts extend outward from the upper chambers. Passages change direction. Roofs are constructed in different ways. Some spaces were accessible to explorers centuries ago. Others were discovered only after people cut or forced their way into places the original builders had sealed. This architecture has generated arguments almost from the moment modern investigators began mapping it. Were particular spaces ceremonial? Were some features structural? Were certain passages abandoned during construction? Did the internal plan change while the monument was being built? Those are archaeological questions, and unlike claims about hidden machines or encoded energy systems, they can be tested against physical evidence. The difficulty is that almost all of that evidence is trapped behind stone. A pyramid is not a building that archaeologists can simply dismantle to inspect lies behind each wall. Any destructive investigation risks damaging one of the most important monuments on Earth. So for most of modern history, researchers faced a basic limit. They could measure the spaces they could enter. They could infer what lay beyond them. What they could not do was see through the pyramid. That limit began to change when scientists stopped asking how to open the monument and started asking how to look through it without moving a single block. And to do that, they turned to particles falling continuously from the sky. The particles are called muons. They are created high in Earth's atmosphere when cosmic rays collide with atoms in the air. Muons are constantly passing through us, through buildings, and through the ground. Most go unnoticed because they interact only weakly with matter. That makes them useful. A thick mass of limestone absorbs more muons than an empty space. So if detectors record an unusually high number arriving from a particular direction, that can indicate that the particles crossed less stone than expected. In principle, it is similar to an X-ray. In practice, the Great Pyramid is far more difficult. Researchers cannot place an emitter on one side and a detector on the other. The pyramid is too large, and the particles are coming naturally from the atmosphere. Scientists must collect them over long periods, reconstruct their paths, compare the measurements with models of the known structure, and look for excess counts that might reveal lower density regions. The technique had already been used in archaeology decades earlier. In the late 1960s, physicist Luis Alvarez and his team installed detectors inside the Pyramid of Khufu, hoping to find unknown chambers. They found none. That negative result was important. Muography had shown that it could test a pyramid without drilling through it. Almost half a century later, detectors returned to Giza with much better technology. The ScanPyramids project began using several non-destructive methods on the major pyramids. Infrared thermography searched for unusual temperature patterns on the surfaces. Muon detectors were installed in different positions. The goal was not to prove a particular theory. It was to search for density anomalies that the known architectural plan could not explain. The first signals were intriguing, but they were also easy to misunderstand. In 2015, infrared measurements identified thermal differences on parts of the Great Pyramid. One area on the eastern side showed a particularly strong temperature anomaly. A thermal anomaly does not automatically mean a hidden room. Different stone types can heat and cool at different rates. Air movement can affect temperature. Gaps within masonry can also create unusual patterns. Infrared imaging can tell researchers that something may be different behind the surface. It cannot tell them what that difference is. Muon imaging offered a much deeper look. One set of detectors was placed inside the Queen's Chamber. Other systems observed the pyramid from different locations. Researchers collected data for months. Then an unexpected region began appearing above the Grand Gallery. It was not part of the known plan. The signal suggested a substantial region with significantly less density than the surrounding limestone. The team did not rely on a single instrument. Different detector technologies were used. They were operated by separate groups. Their measurements were taken from different positions. The same anomaly appeared again and again. In 2017, the researchers published the result in Nature. They called it the ScanPyramids Big Void. The name is intentionally cautious. It does not call the feature a chamber. It does not call it a corridor. It does not assign a ritual function. Void describes what the detectors can actually establish, a large region containing substantially less material than the solid masonry expected in that location. Its minimum length was estimated at roughly 30 meters. That makes it comparable in length to the Grand Gallery below it. Its position immediately created questions. Grand Gallery is one of the most remarkable spaces inside the pyramid. It rises steeply through the monument with walls that step inward as they climb. Above it, the newly detected void occupies a region that earlier internal maps had treated as essentially solid. For more than a century, scholars had drawn increasingly precise plans of the Great Pyramid. Those plans contained the passages people could enter, the chambers explorers had reached, the structural spaces that had been opened. Now the map had to include something no person had ever seen, and that produced a strange reversal. The discovery made the pyramid more visible and less understandable at the same time. Muon imaging could tell researchers that the space existed. It could estimate its scale. It could constrain its position. It could not show a carved wall, a floor, an entrance, an inscription, or an object lying inside. The detector sees density. Archaeology needs architecture. That gap between the two is where the real uncertainty begins. The big void could be one continuous space. It could consist of multiple smaller spaces close enough together to produce a similar signal. Its orientation resembled the Grand Gallery, or it may differ from it. Its internal geometry remains unresolved at the level required to determine its purpose, and purpose is the hardest part. A large empty region inside a pyramid does not automatically imply a secret chamber intended for burial. Builders create voids for many reasons. Some spaces can reduce loads, some can result from construction sequences, some can separate structural elements, some can serve as access routes that were later sealed. Others may have had ritual meaning that cannot be reconstructed from geometry alone. The Great Pyramid already contains examples showing why caution matters. Above the king's chamber are a series of spaces often called relieving chambers. Their existence is related to the massive structure above the chamber and the way loads are distributed through the masonry. These are real internal voids. They are not hidden treasure rooms. Elsewhere in the monument, changes in passage geometry suggest that the builders were solving architectural problems while managing an enormous volume of stone. So the first question after the big void was not, what did they hide there? It was more basic. What kind of space is it? To answer that, researchers needed information muons alone could not yet provide. They needed shape. They needed boundaries. They needed to know whether anything connected to it. And ideally, they needed a way to see inside without cutting through meters of ancient masonry. For the big void, that access did not exist. Not yet. Elsewhere in the pyramid, another anomaly was becoming easier to reach. It was smaller. It was much closer to the exterior, and it sat directly behind one of the most conspicuous architectural features on the north face. A set of massive limestone blocks arranged in a chevron above an area associated with the original entrance. muon detectors had indicated that there was open space behind those stones. This time, researchers might not have to settle for a density map. There was a chance they could actually look inside. The anomaly behind the north face chevrons was different from the big void in one crucial way. It was close enough to the surface that researchers had a realistic chance of reaching it without opening a large section of the pyramid. Muon measurements had already indicated a low-density region behind the limestone blocks. The signal suggested an elongated space several meters long. In 2023, researchers published a detailed study of that feature. The measurements pointed to a corridor roughly 9 meters long, with a cross-section of about 2 meters by 2 meters. Its roof was formed by large stones arranged in a chevron, an architectural technique the Egyptians used to redirect weight away from openings below. That alone made the feature interesting. A void beneath a load-relieving structure may not be accidental. The chevrons imply that the builders expected open space in that location. This time, there was more than a muon signal. Investigators found a narrow route through which a small endoscope could be inserted. A camera passed between the stones. A camera looked into a space that had apparently remained inaccessible since antiquity. The images showed a real corridor. Bare limestone walls, a floor, a pitched ceiling formed by the chevrons above. No treasure. No inscriptions visible from the camera position, no machinery, no evidence of a hidden civilization. What mattered was simpler. The scans had been right. A feature that had existed only as a density anomaly on scientific instruments was now visible architecture. That changed the way the other anomalies had to be considered. Muon imaging was no longer merely producing intriguing shadows inside a monument. In at least this case, it had correctly identified a substantial constructed space that earlier maps did not contain. The discovery also sharpened a much harder question. Why was the corridor built? Its position is important. The corridor lies behind the chevron blocks on the north face, near the area associated with the pyramid's original entrance. That location makes structural explanations immediately plausible. The chevrons themselves are designed to shift loads away from the space beneath them. A corridor in that position may therefore be connected to the way the entrance zone was constructed or protected from the enormous pressure of the masonry above. Another possibility is that the corridor was involved in the building process itself. Large monuments are not assembled as if every internal feature is finished first and then buried under stone. Construction unfolds in stages. Temporary access routes can become sealed. Plans can change. Spaces can survive because they were useful at one stage of construction, even if they were not intended to remain accessible afterward. There is also the possibility that the corridor is connected to another architectural feature that has not yet been identified. That is where caution becomes essential. A corridor leading toward an unknown region sounds like the beginning of a hidden chamber story. Researchers have not demonstrated that this passage opens into a royal chamber, a treasure room, or the Big Void. The fact that two explained spaces exist inside the same pyramid does not mean they are connected. Geometry has to prove that. Until it does, connection remains a hypothesis. And this is one of the places where the Great Pyramid attracts explanations much faster than evidence can support them. The monument has almost everything required for mythology to grow around it. It is enormous. Its age is difficult to emotionally grasp. Its dimensions are precise. It contains sealed spaces. Some of those spaces were discovered only with modern physics. Put those facts together, and almost any extraordinary interpretation can sound plausible for a few minutes. The test is whether the evidence continues to support it once the mystery is separated from the claim. Take the granite in the king's chamber. The chamber is constructed from granite brought from southern Egypt. Granite contains quartz. Quartz can exhibit piezoelectric behavior under specific conditions, producing electrical charge when mechanically stressed. Those facts are real. The conclusion sometimes built from them is not. The presence of quartz does not demonstrate that the chamber was designed as an electrical generator. To establish that, researchers would need evidence of an intended electrical system. Components, conductive pathways, outputs, residues associate technology, or an archaeological context showing that such a system existed. None has been demonstrated. The same problem appears with acoustics. Stone chambers resonate. The dimensions and materials of a room affect the frequencies that become amplified inside it. The king's chamber is no exception. Sounds produced there can create faint resonance. So that is an acoustic observation. It is not by itself evidence that the chamber was designed as a machine. Ancient architecture can have acoustic effects without acoustics being its primary purpose. Ritual spaces can also be designed with sound in mind without becoming power systems. The function has to be established independently. Then there are the narrow shafts extending from the king's chamber and the chamber traditionally called the queen's chamber. For generations, people have tried to explain them. They have been called ventilation shafts, symbolic passages, stellar alignments, ritual channels, and parts of more elaborate mechanical theories. Some astronomical interpretations deserve serious attention. Researchers have proposed that certain shafts were oriented toward regions of the sky associated with stars that carried religious significance in ancient Egypt. The broader idea is plausible within Egyptian funerary belief, where the king's relationship with the heavens, especially the circumpolar stars, was important. Even here, precision matters. A proposed astronomical alignment is not proof that every shaft had one exclusive purpose. Their geometry is complicated. The lower pair do not simply open to the exterior in the same way as the upper shafts. Their ends and internal routes differ. Measurements have been refined over time. Interpretations depend partly on how the ancient sky is reconstructed and which religious texts are considered relevant. The responsible conclusion is not that the shafts have been completely explained. It is that an astronomical or symbolic role is a serious hypothesis, while mechanical claims require evidence that has not appeared. Mathematical claims create a similar trap. Measurements of the Great Pyramid can produce relationships close to familiar constants and proportions. The ratio between perimeter and height has often been compared with pi. Other dimensions have been linked to the golden ratio. The numbers are interesting. Intent is harder. A geometric relationship can emerge because builders chose a particular slope or proportional system for practical, aesthetic, or symbolic reasons. If that relationship happens to approximate a later mathematical constant, the resemblance alone cannot tell us whether the constant itself was consciously encoded. To demonstrate deliberate encoding, we would need evidence from the builder's mathematical tradition, repeated design rules, texts, or patterns that clearly distinguish intention from coincidence. The surviving evidence does show that ancient Egyptian builders possessed sophisticated practical mathematics. It does not require a lost global science to explain the monument, and this distinction leads directly back to the hidden spaces. The Great Pyramid is most interesting when we stop demanding that every anomaly proves something enormous. The Big Void does not need to contain a machine to matter. The North Face corridor does not need to lead to treasure to matter. Their existence means that the internal architectural map of the Great Pyramid is still incomplete. That statement is already remarkable. One of the most surveyed ancient monuments on Earth still contains constructed spaces that were not part of the accepted internal plan until 21st century instruments detected them, and the corridor provides an important lesson about what may come next. A scan can reveal a density anomaly. Multiple instruments can confirm it. A camera can sometimes turn that anomaly into visible architecture. Only then can archaeologists begin answering questions about construction details, surfaces, connections, and function. For the Big Void, that final step has not happened. No camera has entered it. No person has seen its walls. No inscription has been read from inside. No object has been recovered. Its purpose remains unknown. That is not a weakness in the evidence. It is the boundary of the evidence, and once that boundary is respected, the mystery becomes more precise. The question is no longer whether the Great Pyramid hides impossible technology. It is whether modern imaging can reconstruct an architectural plan that its builders sealed behind millions of tons of stone, and whether that plan will eventually explain why the largest unknown space yet detected inside the pyramid was built at all. The next breakthrough may not come from opening the Big Void. It may come from seeing it more clearly. Muon detectors are already capable of distinguishing regions of different density through enormous quantities of stone, but resolution improves slowly. The particles arrive naturally. Researchers cannot simply turn up the signal. They need time, multiple viewing angles, carefully modeled backgrounds, and detectors positioned where the geometry of the monument makes useful measurements possible. Each improvement can narrow the possibilities. A long continuous cavity would produce one kind of pattern. Several smaller spaces could produce another. A horizontal feature would differ from a sloping one. If future measurements constrain the Big Void's shape precisely enough, researchers may be able to compare it with known structural elements elsewhere in the pyramid. That comparison matters because the most conservative explanations are also the easiest to underestimate. Ancient builders working with millions of tons of masonry faced a structural problem on a scale almost without precedent in their world. Every chamber interrupted the mass above it. Every passage created a weakness that had to be managed. Every large internal space altered the path by which weight traveled toward the ground. The builders clearly understood that problem. Above the king's chamber, huge granite beams form a sequence of spaces beneath a massive limestone roof structure. Above the original entrance, chevron stones redirect pressure around the opening. The grand gallery itself is built with a corbelled form in which successive courses project inward as the walls rise. These features do not tell us that the Big Void is structural. They tell us that structural voids belong in the range of serious explanations. One possibility is that the space helped manage forces above the grand gallery. Another is that it reflects the construction sequence around that enormous sloping passage. It could also represent an architectural feature whose role was temporary during building and became sealed when the monument was completed. Each hypothesis makes predictions. A load-relieving space should have a geometry that makes sense relative to the masonry below it. A construction passage should connect logically with areas where workers needed access. A design chamber should show more deliberate architectural boundaries. The challenge is that muons can reveal density without revealing finish. They cannot yet tell us whether the walls are rough or dressed. They cannot show tool marks. They cannot read inscriptions. They cannot tell us whether the floor was intended to be walked on. That is why the North Face corridor matters so much. It demonstrates what happens when one additional type of evidence becomes available. Before the camera entered, the corridor was an anomaly. Afterward, researchers could see its walls and ceiling. They could confirm its architectural form. They could compare the visible space with the chevrons above it and with the surrounding entrance zone. The uncertainty did not disappear. It became narrower. That is how archaeology usually advances. Not with a single revelation that overturns everything, but with successive constraints that make some explanations stronger and others harder to defend. And that is why treating the pyramid as a choice between completely understood and utterly unexplained misses what makes it scientifically interesting. The evidence does not support either extreme. We are not looking at a monument with no historical context. We know the ruler associated with it. We know the society that built it. We have evidence for labor organization, quarrying, transport, surveying, stoneworking, and the broader funerary landscape of which the pyramid formed a part. At the same time, knowing who built a monument does not mean understanding every decision inside it. The two ideas are perfectly compatible. A structure can be historically well understood and architecturally incomplete in our maps. The Great Pyramid is both. There are also questions that may never have a clean answer. Even if researchers eventually image the Big Void in much greater detail, Geometry alone may not reveal intent. Suppose future scans show a long, narrow space with no connection to any chamber. That might support a structural interpretation. Suppose instead they reveal a carefully constructed corridor or a distinct chamber-like form. That would shift the debate immediately. If a robotic camera could one day enter without damaging the monument, details invisible to muography could become decisive. A finished floor, masonry joints, construction marks, deposits of dust or debris, a blocked continuation, inscription. Any one of those could transform the question. Yet access is not simply an engineering challenge, it is also a conservation decision. The pyramid has survived for more than 4 millennia. Every new opening has to be weighed against the possibility of irreversible damage. The most exciting experiment is not automatically the most responsible one. For now, the Big Void remains sealed. That leaves us with an unusual situation. We know it is there because particles created high in the atmosphere pass through the pyramid every second. We know it is substantial because independent detector systems observed the same excess of muons. We know where it sits relative to the known interior. We do not know what its surfaces look like. We do not know whether it is a single space. We do not know whether anyone was meant to enter it, and we do not know why the builders left that volume inside the monument. Those are real unknowns. They are enough. Modern physics has now added a new layer to that documented history. It showed that even after explorers, engineers, archaeologists, and surveyors had spent generations studying the pyramid, the accepted map was still incomplete. A corridor remained hidden behind the north face until detectors found it. A much larger void still waits above the Grand Gallery, visible only through differences in how cosmic particles pass through stone. Perhaps future scans will show that it served a practical structural purpose. Perhaps it belongs to a construction sequence we do not yet understand. Perhaps its architecture will force researchers to revise how the interior was assembled. Any of those answers would matter. The important point is that we do not have to choose one before the evidence does. For 4,500 years, the Great Pyramid has survived while the tools used to study it changed completely. Sight lines and hand measurements gave way to precision surveys, infrared cameras, and now particles born in the upper atmosphere that can map spaces no human being can reach. Better instruments have not made the monument vaguely more mysterious. They have made its remaining mysteries more specific. Somewhere above the Grand Gallery is a large space built into the pyramid and sealed from the world. We can detect it and constrain its position, but we still cannot see its walls or explain its purpose. Until the evidence goes further, the most accurate answer to why it exists is also the simplest. We do not know yet.